Welcome to Ask and Learn.
Okay, so for this problem, we're given that a connected graph with no simple circuits is called a tree, which is its definition. We claim that a simple graph is a tree if and only if it is connected and the deletion of any of its edges produces a disconnection. So this is going to be a standard if and only if proof, which means that we are going to have two directions. We're going to have one proving the going from left to right, and then we're going to have one going from right to left. So for the left, going from left to right direction, one of the things that we need to know is that before we get started, we're going to let T be a tree that is a simple graph. And then so we can identify any variable or any letters that we're going to be using. So if T is a graph that is a tree, then it is connected with no simple circuits. So we want to make sure that we identify how we're defining T. So we know it's a graph. We know it's a tree because it is connected and no simple circuits. Now, what I want to do is I want to throw in another. So we're going to say suppose an edge E exists connecting to T. What I want to do is I want to put in what happens if it gets, so if E is deleted, so what I want to do is I want to kind of put a negation here. So if E is deleted and T is still connected, then T is part of a circuit. So if it's a circuit, then it can't be a tree. And this is a contradiction. So deleting an edge would create, So deleting an edge must break the connection if T is a tree. And that's the end of that side. So then we want to do the other side. So we're going to kind of follow the same thing. So we're going to say suppose edge E is deleted and as a result is not connected, then T is not a tree. So deletion of an edge would negate the statement. And we are done. So we need to conclude out our final statement. So thus, a simple graph is a tree if and only if it is connected, but the deletion of any edges produces a graph that is not connected.